Welcome to the second in our series of webinars presented by DEWESoft USA. The theme for this webinar is an introduction to digital measurement. It is intended to provide a very broad overview of where these devices originated and how they work, with an insight into some of the technologies as well as covering some of the issues that you may encounter and possibly subsequently address. We begin with a little background, some of the historical evolution of these devices. Then we will look at how the systems that we use today take the responses from our sensors and convert them into digital representations of what they're measuring. The next subject addresses resolution as well as measurement range relationships and the process of quantization. And finally, we will review a couple of the most common pitfalls and issues that are associated with using digital measurement systems. But before I get started, I would like to touch on the subject of acronyms. Unfortunately, you're about to see quite a lot of them. I always consider them to be a convenient way to save ink. Of course, we're all discouraged from printing anything unless it's absolutely necessary, but still we advocate the use of acronyms in our speech. Perhaps it is so those of us who are frequently accused of speaking too quickly can enhance the speed yet further, and I did do that on purpose. As sad as it is for me to admit this, but I do have a favourite. Unfortunately, its use has stopped since the technology has all but disappeared. However, for those of you who are old enough to remember it, it is PCMCIA. It's one of my favourites, and not just because it's one of the longest, but because it's almost poetic. PCMCIA, which actually stands for Personal Computer Memory Card International Association. But the reason why I am so fond of this acronym is because of a good friend of mine, Dr. Peter Blackmore, who informed me that it really stands for People Cannot Memorize Computer Industry Acronyms. Now, just a quick shout out for the infamous acronym that another friend shared with me, and that is one that I believe should be universally adopted, TLA, which of course stands for three-letter acronym. So basically it's a three-letter acronym for a three-letter acronym. To the history. Historically, measurement systems have been around for centuries. In fact, there is evidence of an ancient system in Syria that dates back over 1,000 years BC that was used to meter water, possibly because it was around the time of the last significant climate change event and water may have been scarce. The rather odd-looking device on the left is actually a seismometer dating from AD 123, and it is claimed that it was so sensitive it could detect earthquakes from hundreds of miles away. The other images are of Edison and Muirhead's devices, the phonograph and the telegraph recorder. Now, I must confess I added the squiggly lines on the telegraph recorder for a bit of fun. It really kind of printed Morse, if anything. The one thing that all of these have in common is that they all have storage media, be it sand or liquid into frogs, or scribes into wax, or holes into paper. And just a final little comment. It's kind of funny. I bet nobody ever heard of a solid state frog storage media before. Before we went digital and we were transitioning from paper and wax media, we used tapes, ferrous oxide to be specific. Fundamentally the same stuff that was used in VHS, Betamax and audio cassettes, if anyone remembers them. And somewhat ironically, magnetic tape theoretically could have a resolution, and we will cover resolution a bit later on. We could have a resolution that significantly exceeds that of any digital system today. However, there simply wasn't, and possibly never will be, the technology to read and write to that level. Besides, at some point someone had to be able to use that data for analysis, which meant it either had to be digitized or transferred to some sort of media anyway. My story regarding that matter is when I first got involved in DAC, I visited an early adopter of digital technology, and they had one of the first digital systems in the US. When I arrived at their facility, I was horrified to see the digital system bolted to a bench and hooked up to tape-based DAC. They were still using the tape systems for their tests because they were afraid to go completely to the digital system and were using the digital systems to digitize their tape data. I guess prior to that they'd used thermal paper digitizers for their tapes. Now, most tape recorders in measurement use reel-to-reel, but later some even use cartridges very similar to the old video cassettes. Now, this image is to bring a margin of reality to the way it was. There are some of us that can remember using paper reels or tape to tape, but I doubt there are many left that remember doing their analysis like the guy in the image. I doubt there are many folks that left that even know how to use a slide rule. One important point to make is, in the image, the storage medium is his head and the paper. And just a quick question to everybody, would anybody like to generate an FFT using that method? It's worth having a little insight into the chronology of digital processing, if for no other reason than to appreciate the huge leaps that have happened in just the past 20 years. Which is ironic, as some folks are still using DEC systems that were designed over 30 years ago. Now, as you can see, it really started in the 50s with Gordon Kidd Teal at Texas Instruments. Then between Jack Kilby's first IC and Mohammed Attalla's passivation process, it went in huge steps, and today we of course all know about the multi-core processors and probably have a monster machine at home for our games. The image in the lower right may be of interest, as it was actually an early IC that was used in the Apollo space missions, and it was actually part of their guidance systems. But it isn't until you draw graphs illustrating the incredible progress in processing speeds that you really appreciate how things have advanced. From about 0.64 MIPS in the late 50s to 22,800 MIPS in 2005. And keep in mind that a MIP is 1,000,000 instructions per second. And viewing this chart will hopefully bring into perspective the comments I make about DAC systems that were designed 30 years ago. It illustrates to some degree why they were somewhat limited. Now, how does that look from a measurement point of view? Well, the paper disc was introduced in the 50s, and honestly it's still being used today. Low sample rate applications like thermal monitoring and power generation systems, etc. still use them, and they still work very well. But the first commercial, truly digital data acquisition system, the Datamite, appeared in the very early 80s, which was initially a single channel, and I want to use the words wonder machine, and not least of all because it could actually process and store rainflow counted data. Then in the early 80s came the very first high channel count, truly digital multi-channel integrated DAC, the Mega DAC. The first ones actually had 5¼ inch floppy disk drives. Then later on it went to solid state and optical drives. But how many people actually remember the 5¼ inch floppy drives? Again in the early 80s, the brainchild of Professor Norman Miller and Professor Darrell Sosi of the University of Illinois, the SOMAT 2000 series field computer arrived, which was initially a single channel per layer. And to get things into perspective, a 256 kilobyte memory module was about $4,000. Forget the price for a moment, because you have potentially 130,000 times as much memory in an iPhone with 32 gigabytes of RAM. So just take a moment to imagine how much you would have paid for that iPhone if memory prices hadn't gone down. Then in the early 90s, along came the SOMAT EDAC, which was one of the most successful DAC systems in the world and was incredibly advanced for its time. Of course, that was over 30 years ago. And finally, to the DEWESoft Sirius, which began life in the mid-2010s and combined not only all of the advances in technology, but introduced some unique technologies such as parallel or dual-core ADC application. And we will cover that technology a bit later on. And just to quantify here, there is 34,359,720,775 bytes in 32 gigabytes compared to the 256,000 bytes in that $4,000 memory module. So I wanted to end this section on background with a little added getting things into perspective, at least to show a more realistic size comparison for these devices, because one thing that has happened with many of these advances, as with much innovation, is the reduction in overall size. The volume of a full-size Mega DAC is enough to fit about 20 Sirius modules in, and that is a potential of a total of about 320 channels in the same space as 64 then. And to end, let's not forget that size was probably not even a thought not so long ago. Now let's have a look at how the signals get handled inside the systems. I won't read this entire text, but what we will do is we'll introduce a couple of acronyms. DSP, Digital Signal Processor, and FPGA, Field Programmable Gate Array. You've probably heard of these anyway. All we need to say is that these devices are incredibly powerful if they're in the right hands. And I say that because a DSP is basically like a massive library. All you have to do is, well, write all the books and then lay them out in logical, efficient and a meaningful way. And don't forget to keep all the volumes together. And, well, actually, to contradict myself a little bit, some of the books may have already been written. For example, a DSP often contains some predefined functions. A common one is the finite impulse response filter. But, of course, you still need to know where it is and wait for it, using our book analogy, be able to read and take advantage of that information. So using the library analogy, this is really just to illustrate how vast that library could be. Imagine each of these blocks is a technical section in your library, and each of the smaller blocks is a series of bookshelves, on each of which there are a complete set of volumes. Then you need to traverse your way back and forth as you read each volume at the reading desk after you've checked the reference manuals in a different section. And coincidentally, you need to do that at about 1/6 the speed of light. So a little background on DSPs and FPGAs, as mentioned before. I said that things have been shrinking. So this is obviously this type of technology has shrunk as well, and a DSP is about 1/10 the size it was 30 odd years ago. The other thing is that these are really specialized devices, and only a handful of people even make them. TI-AD, Motorola, and so on. The thing that a DSP does is really simplified by some folks into two categories: multiply and accumulate. The MAC in DSP means multiply and accumulate. And because of this, it has to be able to move things around effectively from this buffer to that buffer. And so memory had to be fast enough to handle it. Oops, sorry, wrong kind of RAM. It's one of the many reasons that memory has gotten really fast over the years. It's the demands from the DSPs, processors and GPUs, for example. In fact, memory now is faster than ever and often needs its own dedicated cooling systems. The image in the lower center is actually a description of the DSP FPGA implementation on one of the many interface fixtures at the CERN accelerator in Switzerland. As far as ADC technology is concerned, there are really only a handful of types. You may have heard of Sigma Delta, sometimes called Delta Sigma, and or the SAR, Successive Approximation Register, but there are more, the OSAR, the CADC or Capacitive ADC, but they rarely figure in our world. So let's take a very brief look at the two most common. The Sigma Delta is the mainstay. It is proven and has probably the most airtime in our industry. It is really a single bit that is overclocked, although you shouldn't relate that phrase to what you may have done to your home games computer. It has almost nothing in common. The overclock is really the sample clock. It is the bit that tells the ADC when to take a sample. In a Sigma Delta, it is typically at least twice, and that's good old Nyquist there, what you really want. And oftentimes it can be many tens or even thousands of times faster than what you actually see being available to you for recording. Now, the nice thing about the Sigma Delta is that it actually characterizes every single signal individually. That is to say, it has a shaping function built in. That means as long as you are sampling fast enough, it is going to represent your signal exceptionally well. Now, the SAR is as different as night is from day. It is really akin to a state machine. It looks at the incoming signal and basically matches it to a binary representation. The good thing about that is it doesn't try and shape it. Now, if that sounded a little contradictory to what the Sigma Delta is doing, well, frankly it is. And that is because SAR and Sigma Deltas are better suited to specific test applications. But how do you know which one is the most appropriate? Well, you don't have to. Later on we'll cover sample rate issues and you can see where this is going. And we will also be having an ADC webinar later that you're more than welcome to sit in on, and we will go through the pros and cons at that time. But do keep in mind that some advanced systems can be either or even both of these. So let's have a quick review of how your signal got placed onto your display in X3, for example. So we begin with our analog signal, and this gets passed into what some folks call the first stage, which may comprise of an anti-aliasing filter, which is usually a low pass, such as a Butterworth electrical filter, and then an initial gain. The outcome of that first gain is then subjected to a secondary filter that you, the user, would typically define. This could be almost anything depending on your system and its capabilities. That is then corrected for any offset, as you don't want to sacrifice a side of your signal because the bias prevented your second gain from being set to a higher level because it would have clipped the signal. The second stage of gain is then applied. Now, this is mainly because most ADCs have specific input voltage ranges, such as 2, 4, 5 and 10. You really don't want to put a microvolt signal into a device that potentially wants 10 volts. that would produce a limited number of bits, and we'll cover that in the resolution section. Then we get to the all-important ADC, where the binary is basically created. And finally, we get to the DSP and the FPGA, where all the real computing takes place, and ultimately you get your squiggly lines displayed. Of course, if you happen to have the dual core, well, that's just one of the cores. Different systems have slightly different approaches, but the ultimate conclusion remains the same: to get your initial signal into an accurate representative digital equivalent that you can see and work with. Some systems will offer an analog output. These have almost the opposite of the inbound signal train, with a DAC, digital to analog converter, then an offset correction and possibly amplifiers as well. Now, it's probably worth mentioning that this is considered to some degree to be old technology, as modern systems have added digital lines such as EtherCAT that oftentimes beat the latency of the original analog conversion as well. So effectively removing all of the analog cables and substituting them with a single communication line to the controlling system. So with a test involving, say, 96 channels, where you had to have 96 cables carefully identified, then routed to your controller system, you now have one. Now, this is a very brief mention about both dual core and bit resolution references that people use. We've probably all heard of SNR, signal to noise ratio, DMR, dynamic measurement ranges, CMR, common mode rejection, more acronyms, and of course bit resolutions and references that folks make to that. Well, just for reference, in case you didn't already know, a 16-bit ADC in a perfect world would be about 96 dB, a 24-bit 144 dB. A simple rule of thumb is to simply multiply the number of bits by 6 to get rough numbers. But you may not hear that the reality is that no 16-bit system ever achieved 96 dB for its measurement range. They're generally doing well if they can achieve around 80 dB. A 24-bit is doing well if it can achieve around 115 dB. But using a dual core, you really can achieve about 160 dB, and that's the equivalent of about 27 bits. Ironically, most so-called 24-bit ADCs are really only 19-bit in the first place. Now, I could talk all day about this subject, but again, we're going to have a dedicated webinar, so keep your eyes and ears open for that. So before we end this section, I'd like to make a quick mention of data integrity, which really is a very broad subject. Again, something we will cover in more detail in our future webinar, but I should at least mention it before we continue, because some systems approach things in a slightly different way to others. Think back to a comment I made earlier about the price of memory for a system from the 80s. I bring that up because memory was a premium component in earlier systems and played a big part in how signals were processed to take advantage of limited availability of space. Nowadays, we have the ability to store vast amounts of information and the speed and power to process it far more efficiently. So the approach of some devices is store it all, then reduce it with all the assurances of having the original data and that you're unlikely to miss anything, and that way you don't lose anything. And I mention this because if you have a Sirius, a Krypton, an R8 and so on, that's exactly what it's doing, and you may not have even known it. Okay, the next section will look at the process of digitizing your signals, the resolution and the implications associated with the conversion. Now, we all have computers these days. Some of you may be using 64-bit versions of Windows, and this is really meant for fun, but some may still be using computers that run DOS. Remember that disk operating system? Yeah, I doubt it, but you never know. Anyway, systems have evolved with the technology, and the systems that were produced in the 80s and 90s were predominantly 8 or 12-bit systems, which meant that they offered 256 or 4096 discrete levels into which your signal quantities could be placed. The use of discrete placements is really what the word quantization means. And it should be said that this is okay. The resolution issue really only becomes a problem if you have low-level signals that possibly need to be characterized and, well, as you can see, lose some of their fidelity because there simply wasn't enough space to quantize them into. To get the equivalence and the limitations into perspective, you can see the equivalent quantization of a 4000 microstrain range signal equated to almost 20 microstrain per bit for the 8-bit systems. and rapidly gets close to what I call ridiculous as you increase the number of segments available. If all you were interested in was the high amplitude reversals, for example for your fatigue prediction, this probably will never ever even entered into your thought process. But keep in mind that you really don't get all the range as we alluded to earlier. Now you may have noticed on the previous screen there were actually two ranges, one that said equivalent and one that said reality. These are based on the assumption that although we have all probably clipped data in the past, chances are that we didn't do it on purpose. So we always try to include a safety margin. In this example, the safety margin is 10% of the entire range. So in a 24-bit system, you will have the equivalent of 15 million discrete levels to quantize your data into. If we now take a look at the comparison of the inputs, high and low level signals, and in this example we've used a couple of options available on the STG as a reference, we have illustrated the equivalent of an input of plus or minus 10 volts and plus or minus 1 millivolt, and can see the perfect well quantized equivalence. And you'll probably agree that the outcomes border on oh my territory. In addition, if you have the dual core technology, you could be getting almost this for each in the same signal. Now on the flip side, as seen before, when you try and characterize a signal, you probably want as much information as you can get. Imagine a signal that looks like this that is quantized across only 3 bits of your range. And you can probably see where this is going already. What was potentially, let's say, a loading reversal now appears as a plateau, a perpetuation of the loading condition. And of course, we really don't know what the peak amplitude was. We only know it was somewhere in that 8th bit, noting that each of the quantized levels could span hundreds of microstrains based on our previous comparisons. And by the way, this is what people refer to as the quantization error. Again, with the addition of the second core, you effectively retain both the high and the lower level data. But with a single core, you may have to sacrifice your low level quality. And if you look at the screen, you'll see what the data really would have looked like if you'd have been able to quantize to a greater degree of accuracy. Okay, enough about resolution, quantization and bit issues. Let's take a look at some of the most common yet to a large degree avoidable issues and pitfalls. Now, there are some things that simply can't be avoided. For example, if your testing is in the desert, there is a good chance that thermal effects are going to be seen virtually everywhere. So if you imagine your real signal looked like this based on some dynamic event, but there was also an ambient change in temperature during the course of your test, it could have resulted in a DC shift that looks something like this. Now keep in mind that this is potentially everywhere, where your sensors are, where your cables are being routed, as well as where the actual measurement system is. Now there are a number of approaches you can adopt to at least mitigate these effects. One is of course to insulate everything from the thermal changes, and that is of course totally impractical for the vast majority of testing. Or you could simply measure the ambient changes and make an educated assessment of their influences and basically remove them. And or you could take advantage of the tools at your disposal. For example, if you have sense lines available, you could use them to compensate for thermally induced resistance changes in your sensor cables. And of course, do everything you can to minimize the thermal changes at your actual measurement device. Just being cognizant of these influences on your measurement is the really important thing to take away from this. Try and avoid the Rumsfeld effect. And that's kind of disrespectful, because frankly what he said actually kind of makes sense, I think. And don't worry, I don't plan to talk extensively about this table. It's just something that I put together for the US Air Force because they were measuring components mounted on aircraft that were being subjected to what can only be described as massive changes in temperature in extremely short periods of time. As in, they were parked in very hot environments, then cruising at extreme altitudes, therefore extremely cold temperatures, in a very brief period of time. The one highlighted section really puts the purpose of sharing this into context, since it's something that can happen frequently. I've even seen it here in the US, and I live in Michigan. The example is a 50 Fahrenheit temperature change, and it could amount to a 350 microstrain offset, assuming your cables were 35 foot long. Let's cover something that being an old guy I am particularly passionate about, mainly because I'm old enough to have been in test during the evolution of these technologies. And that is, of course, aliasing. Now, we've probably all heard of this. We may even have been the victim of it. The fact is that, ironically, quantization is effectively the art of aliasing your analog data into digital equivalents in the first place. But in these examples, we can see that there is enough resolution to capture all, or at least enough, of what we want. You'll probably notice that the sinusoidal shape is easily discernible in all three of these. In fact, if we were interested in frequency, we haven't missed a thing. If the window is 1 second, we can see 3 Hz across all of them. The arrows at the bottom indicate the sample points. Now, if we slow it down a bit, to a large degree, we can still see the frequency in the upper image, and to a lesser degree in the center image. We can see the amplitude in the upper image to a certain degree, and we can see most of the amplitude. If we were looking for peak excursions, then we certainly would have got it statistically in even the second one. But in the third one, as you can see, it's fundamentally a total loss. So this screen is really just to illustrate that quantization of the signal. It really just illustrates what's going on under the hood. So what you've got here is you've got an inbound signal that's being sampled, it's being quantized, and then it's being stored. So this is really just to illustrate what's going on this is part of what you will never see because you can't get down to a microscopic level and look at the electrons flowing around. Signal aliasing. Of course, the most common human exposure to aliasing is our very own AC system. It's actually cycling at 50 to 60 Hz typically, depending on where you are in the world. We of course don't see it because we actually only process images at 20 to 30 frames per second. You've probably heard stories of people seeing things in slow motion if they're involved in an accident. And this is most likely because our bodies create high levels of adrenaline and the entire processing portion is accelerated. It's the kind of fight or flight, the animal protection system in us kicking in. Now, the next most common form is visual aliasing. And the movies used to use 25 frames per second because it sort of matched our processing speed and was enough to make the actually static images appear to move. In fact, if you look at some of the old original Disney movies, a cunning method of only animating every other image was used to take advantage of our processing speed and actually made the animations appear much smoother. Now, you'd have to dig around to find some of the original movies, and a lot of the digitized ones have obviously compensated for that. Now, the animation you're looking at on the screen was created using a CAD application, and you will have to take my word for it that there's no trickery at play here. The handle is fixed to the sprocket on the left and is obviously rotating in a counterclockwise direction. Now, unfortunately, because PowerPoint cannot handle the frame rate very well, it's actually much slower than it really is. Note that the rotation rate increases, then decreases. But keep the handle in mind as a reference to the sprocket, because what we're going to do now is we're going to use 50% less frames. And it actually appears to be fine. Now, that's partially because, funnily enough, PowerPoint can handle this. But we are now going to reduce it by 50% again, and I'd like you to pay careful attention to the handle. So you will see that the handle is still rotating as it was. But if you watch closely enough, you will see that the direction of the sprockets appears to change. So watch carefully where the sprockets are meshing and make a note of what you see. Now, that is something that is virtually transparent to us. It's almost impossible for us to discern the point at which the rotational direction changed. And this is about 25% of the actual rate. Now we're going to reduce it by 50% again, and you can see once again the handle is rotating in the counterclockwise direction and is still very clearly definable as rotating that way. But the sprockets at this point appear to be kind of rocking a little bit. They're not really rotating. And if we go yet further, it now becomes completely impossible to tell that those sprockets are rotating. This is visual aliasing. Now, just to reinforce this, I found this video, which I thought was a particularly good example, because not only is it funny, but, well, and the fact that somebody went to the trouble of building a wheel with sneakers, which is incredible. But what it really shows is those sneakers almost going stationary on the ground at times because the frame rate isn't fast enough to capture all of the images. Not that we would be able to see it in this anyway. Okay, To illustrate the effect in our world, I've got 4 sine waves. One at 15, one at 50, one at 100 and one at 200 Hertz. And I'm going to combine those into one. And a quick challenge as they compose themselves in the composite. Which frequencies do you think you can see in the composite? Now most people quickly see the higher frequencies. Some see the lower frequencies. Not many see the lowest frequency. It's like those magic eye pictures you may have seen. Some people see it, some people don't. I have the benefit of being an old guy and losing my eyesight, so I just say to people, oh, I need new glasses. Anyway, we're going to use this data in just a moment. But before we do, I just want to go through this. We use tools such as discrete Fourier transforms, or FFTs, shall we say, to extract frequencies from spectral data. Now, they're often termed as fast Fourier transforms because they're fast. No, that's not really the reason why they're called fast. Well, anyway, a DFT and an FFT are basically the same thing anyway. They're both trigonometric series that represent the frequencies from some spectral data. Now, I created this animation just to illustrate what the Fourier transform looks like if you reverse what we did on the previous screen, a sort of under-the-hood representation. And there is, of course, a few more sine waves in this example than there was on the composite we just created. This was intended just to be a tad more representative of spectral data rather than clearly definable sine waves. But if you've ever wondered what it looks like behind that FFT, if you grab your laptop and turn it sideways, you still won't be able to see this. Okay, so here's the combined signal and a subsequent Fourier transform. And what we're going to do here is we're going to drop each of those in just to illustrate where they sit within that Fourier transform window. Ironically, you may see some visual aliasing as they drop into that screen. So there's our frequencies. Now, herein lies the problem. As you saw with the sprockets, at times they appear to change direction, and at others almost stopped rotating and sort of rocked. Now, if we take that combined set of sine waves and sample too slow, we actually see the same thing in our data. So here we're sampling a wee bit too slowly, and then at the bottom of the screen you can see we've got a frequency that was not one of the ones we were looking at originally. And there is the problem. So how do we avoid that sort of thing? Well, we can use a thing called a TRM, shall we say. And it's really just so that we can understand as much as we can about what we're measuring. After all, you don't use a 6-inch rule to measure a 30-foot piece of timber. Well, maybe you do if you drank too much of the weekend, but that's another story. So rise time becomes an incredibly important component in making certain determinations. But I hear you ask, how can we? Let me show you. If you have available to you a system and some nice, easy, intuitive software, you can make much of these determinations in literally a few moments. And this could save you some concerns later. So this is worth doing from time to time as a matter of course anyway. And these are just suggestions, by the way. And I emphasize the word suggestion. I'm not advocating that you delay a test so you can confirm what someone said was right or wrong. So this is just a suggestion. Okay, what I've done in this suggestion is all I've done is set up a very simple single channel with a user input to control when I store my data. Keeping in mind that if you want to see as much as possible, you should set your sample rate as high as possible. Now that's assuming that your sensor has capabilities to go to those ranges. And don't forget that some sensors are only rated to specific frequencies. There's little point in trying to sample something at 200 kilohertz if it's rated to 20 kilohertz. And as far as the data is concerned, don't worry, you can always delete it later, and it shouldn't be that much anyway. Now, what I've done is I set the triggers to be my user input, and since I'm confident I can get enough data in a relatively short duration test, I've set it to capture only 10-second blocks. And you may also notice that I set it to do a multi-file set, again, just to keep things in order. And then all you do is run a few quick tests to gather some data. And in this series, I'm going to start with a static data. In essence, the test object completely untouched and unaffected by anything other than the natural surroundings. Now, you could even do this with the excitation turned off. That way you even remove possible effects from the power coming from the measurement system or possible ground loops. And you may want to do this just to become familiar with what does happen when you electrically excite your sensors or not. In step 2, I'm going to use a hammer or some other mechanism to provide a sort of controlled wave through my test specimen. We want to see what frequencies are involved in that propagation of the wave as it passes through the specimen. Again, you could repeat this step across connected components to gather information about the coherence between them. It could also demonstrate where dampening might improve the behavior of a test object, but we'll cover all of that in a seminar on modal analysis later. And now we repeat the test, but this time we're going to mechanically excite our specimen. So if this was a vehicle, this would be a short drive, for example. You may need to repeat this under different conditions, different surfaces, different tracks perhaps, to characterize your test object, but again, that is something we'll cover on a later webinar. And now that we have our data, we can perform some very quick FFTs on the test data. Firstly, the static, then the mechanical, sorry, not the mechanical, the modal, my apologies, or the pseudo-modal, the one that I excited by tapping it with a hammer, and then finally, the mechanically excited data. And with the mechanically excited data, if it's a vehicle, for example, you might want to do some coast tests as well, by which I mean turn the engine off if it's an internal combustion engine and coast and gather data while it's coasting so that you take out the effects that are being transferred from that internal combustion engine. And then finally, we view all the results together and we look for something common. Large amplitude excursions and of course something we think unexpected. From this we can quickly determine where everything is happening in the frequency domain and whether we have any issues involving noise. For example, emanated noise, radiated noise, AC interference and so on. And from that we can make determinations of how best to set our sample rates and filters to capture the bit that we're interested in. Now there are a couple of simple rules to apply to these. If you're looking for frequency information, you've probably heard this before, you should apply the Nyquist principle and at least double the frequency you're looking for. If the amplitude and characteristics are of importance, for example, because you are planning a structural fatigue test, then use the 10F or 10 times principle and factor your sample rate by 10. Some folks prefer to be safe than sorry and go as high as 20, even higher, to capture what they need. And remember, the greater the frequency, the better characterization of the input signals. Now, I've heard many times that something is sampled at that rate because that is how we do it. While there is in principle nothing wrong with that statement, because somebody probably did these sorts of tests to get that sample rate, or they knew something about the structure or the material. But don't forget that they may have been using some systems with limited capabilities. And with the power that's available to you today, you may be able to reinforce their determinations or, and this is tongue-in-cheek, heaven forbid, challenge their determinations. And I will point out an important statement on this screen. Always remember that you can take away, but you can't add back in. So you can always take away, but you can't add back in, regardless of whether some software suggests that you can. It typically uses something like wave characterizations to make its assumptions, and frankly, the use of the word assumption is always a kind of no-go for me. We all know the breakdown of the word assume, and it will make well, you probably know where I was going with that at any rate. So more is better, and remember, memory doesn't cost $4,000 for 256 kilobytes anymore. It doesn't mean you have to collect all of your data at 200 kilohertz. It means you could collect all of your data at 200 kilohertz, or whatever your system limit is. So in conclusion, although this webinar could have gone on for days, we want to summarize this entire subject in one phrase. The key is simply to appreciate what you use to measure, explore its potentials and have a good understanding of the hows and whys, and possibly push the limits to appreciate why it's done the way it is. Again, after all, you have the tools available to you. And if you don't, talk to your local DEWESoft representative and he'll help you get the best tools for the job.